Hello, everyone. Um, Welcome to this webinar on SimCenter 3D for Space Systems, Accelerating Thermal Analysis and Multi-Physics Integration. I believe my colleague Ganesh is having some internet issues. So I guess I'll start by introducing myself. So I'm Jean-Frédéric Ruel, product manager, part of the product management team for SimCenter 3D thermal multiphysics, more specifically on space systems thermal. I've been at Maya for the past 13 years now as an application engineer and now part of the product management team. And the other presenter today will be Ganesh.
Hi, I'm here. Sorry, something happened with my side. Thank you, JS. My name is Ganesh Natharaman. I'm part of the Siemens SimCenter mechanical team responsible for aerospace and defense. And yes, today myself and JF will walk you through our solutions for the space industry. Of course, most of this will be a focus primarily on the thermal side, but I wanted to spend some time to give a little bit of context of how this capability exists within the overall context. So, you want to go to the next slide, Jeff? Great. So yeah, indeed, one of the key things here is that obviously I think you're all here and we appreciate you coming to understand about some of our solutions for the thermal analysis, but I want to give some context as to why that's important. But within that context, really when we talk about SimCenter as a whole and SimCenter 3D, which is part of SimCenter Mechanical, we look at the space industry from the three primary segments: the launch segment, the space segment, and the ground segment. And I'll explain, and for each of these, we have slightly different solutions. But before we do that, why don't you go to the next slide, JF? And we had some questions that we wanted to ask to just get a feel for the audience members. So we will start a poll over here. And yeah, what we'd like to understand is your business, if you're in the space industry, where you are. So we will see as these answers come in, because as you will see, our solutions, we have different solutions that exist for the different pieces of the industry. Okay, I'm seeing.
Yeah, a good spread. It looks like.
Yeah, exactly.
So we'll just. I think about 50 people. 50% of the people voted. So I think some good participation.
Good yeah, exactly.
So we'll keep going with the. I'll share the results. Yeah, a good spread of the different applications today. So hopefully what we'll have to show will apply to everyone.
Right. And yeah, I mean, I think, okay. Did you,
sorry.
Well, I mean, what I saw from the, yeah, it's okay. I can speak to them. I mean, I think one of the things that we saw there, and if you can go to the next slide, actually, is that we saw a spread between, and one of the big things, of course, is on the payload side, as well as on the launch side. Now, and then in terms of the types of missions that we have. And so again, none of this should be new to you, what you're seeing on the screen, but this is really what we've been seeing, obviously, in the industry. And I think it's safe to say in the last 15 years, the industry has changed radically. Obviously, there's everything to do with launching and the cheaper launch, which has enabled and democratized a lot more companies trying to get into the space industry. But then also there's the potential of manned exploration, and we see more and more of that. And it was interesting to see that some of the people who mentioned different vehicles, exploration vehicles. And then, of course, the continued demand on all these ground-based applications that get more and more niche. Every time we go to different kind of events, we see, whether it's monitoring the earthquakes and monitoring like forest cover, or you name it, there's more categories. So the point is, though, is that we see a lot of evolution here. And should I go to the next slide? And ultimately, the key thing here is that what we see is that, and I think you guys can probably recognize this, but again, this has implications for us as well in terms of the products that we want to deliver. But we see a shift from exploration, and the implication there is that it was mostly used to be government contracts for bespoke products that that large prime contractors would develop, but going more into exploitation, being able to leverage the resources that exist in space in many different ways by having more standardized items such as CubeSats and so on, so forth. So being able to do that and doing that, you need to be able to have flexible methodologies. Of course, in all cases, there's a short development cycle, but as opposed to in the past where we typically saw more of these larger bespoke projects, which had a much larger timeline. Here there's a competitive, positioning. So when it's a bespoke product, you set the time based on the safety requirements and so on and so forth. But here with the competition, you have to go faster, and then the prices as well. So if you go to the next slide. What we see here, and that's why it was interesting to have that poll question looking about launch and the different type of people, is that we see that there's different kind of implications on the payload side and on the launch side. So, I think one of the key things, and you've seen it here, is that, traditional satellite, which is what you can see on the image and on the left, at the size of it versus what is a CubeSat, which is much, much smaller. So, it kind of says here in the statement, that it's creating less expensive satellites in a shorter period of time because of miniaturization, and then they can be democratized. And what we're seeing is more and more customers looking at starting up and doing solutions, but they all have the same challenges. And if you click through, what you see is that, there's the implication is that, of course, the satellites on the one hand are smaller, we have to get there faster, and we have to get there cheaper. And those have implications on how you design your payload. And when we talk about that in all aspects, not just from a thermal perspective, but from a mechanical perspective. Now, if we shift to the second area, which is the launch vehicles, if you go ahead and build this, on the one hand, you can see the different areas of, on the one hand, the cost and the weight, two important considerations. And here, while this topic is about thermal, you'll see that I'm focusing on the structures, and I'll explain why in a moment. But if you continue to build this, JF, the implication is, on the one hand, the structures to the cost is a huge portion, and you still therefore want to be able to reduce that. It's also, the weight is a significant factor, so we want it to be lighter. And the last one, which is of course, the revolution that we've seen, is that the cost of spaceflight, if you build it through, has gone down. So this is showing what it used to be for a space shuttle to what it is now, with thanks to Elon Musk and SpaceX, and now Blue Origin is doing it as well. I think there's one more build, because one of the key things is that there's this notion of durability, and the implication there is that when you were creating a single launch vehicle that would go and then you wouldn't even recover it. It's one thing, it's a single use, but here the fact that you have to reuse it, and there's an implication. Now, I think based on the poll, most of the people are more on the payload side, which is fine. But the reason, going back to why I'm focusing on structures, is that even for the structure, and even when you yourself are developing payload, well, on the one hand, the payload has to fit inside the structure, but also there are also thermal requirements that exist there. And so this kind of leads to, and then the final point I would say is that oftentimes you need to consider a lot of different physics. Within SimCine 3D, you can address things such as deployment and multi-body dynamics. But one of the key advantages that we feel that you have using SimCine 3D is not only are you able to do the thermal analysis capabilities, which JF is going to go into depth with, but you can also do the structural analysis as well as multi-body dynamics and a number of different aspects. And they are all as important. Okay, JF, please go ahead. So really, obviously the point is that to bring this all, that there's an explosion of complexity, lots of complex requirements. And if you click through, broadly speaking, within Siemens, we have the ability to provide you tools throughout the entire process, from product design to product realization. Of course, today the focus is really on looking at the digital twins for the product design. But everything is connected on this backbone of, on the one hand, tight integration to CAD, also tight integration to a digital thread using our ability to access the Space Systems Thermal as well as SimCenter 3D access to Teamcenter. You click the next one. But all of that again, so all of this is provided with
Oops, I think I at least don't, yeah, don't hear Ganesh, but essentially, oh, yeah, it sounds like Ganesh has some internet issues. So yeah, the accelerator portfolio of Siemens sort of combines all of that together for simulation, electronics, mechanical, and that's all one portfolio.
JF, can you hear me again?
Yes.
Okay, great. Sorry about that. I don't know what's happening. Yeah, if you continue to the next slide. Yeah, and so ultimately, you know, the main point that we have here is that we have all of, hopefully you get in a sense of what we see as the challenges. Again, we're not trying to tell you your own challenges, but the implications of that in terms of what we develop as a product. And that we have a number of capabilities throughout the Siemens solutions to address that. But specific to the space industry is that our solutions, and specifically Space Systems Thermal, have been used in the space industry for a long time. And here you can just see some of the customers that use us. You can see on the one hand different agencies, different kind of prime contractors, as well as startups and so on and so forth. So there's a long history of using our Space System Thermal capability and SimCenter 3D in general for all the different physics for, you know, going on 30, 40 years. Next slide. So finally, you know, just to give some context, we talked about all that. If you click through, you know, SimCenter as a whole, so within Accelerator, you have all of the simulation capabilities, which we refer to as SimCenter. And within that, we address a number of different disciplines, as you can see on the wheel there. But if you click through, you can see that these are all the different kinds of aspects that we try to address specific to the space industry: propulsion, safety, and so on and so forth. Now, within our mechanical solutions, the ones that exist with SimCenter 3D, of which SimCenter Space System Thermal is, you can look at the structural analysis, the electromagnetics, and testing, and so on and so forth. And so hopefully that gives you a little bit of context to what you said. And finally, before I hand it over to JF, if we look at this slide, this will provide some bit of a focus, which is that, as I mentioned earlier, we look at the space industry and the challenges in 3 different distinct areas, with the launch segment, the space segment, and the ground segment. And within that, different capabilities in SimCenter 3D can be addressed by different domains here. And today the focus is really going to be, you know, answering these questions. On the one hand, will it survive launch? On the second, once your payload has survived launch, will it then function in space? And that's really where the thermal analysis comes into play. But the key thing, hopefully before I hand it over to Jeff for you to remember, is that the reality is when you're developing and designing your product, you need to take into consideration all of these aspects. And with SimCenter 3D, you have one platform to be able to do that, where you can have one master model that can be done and sent to structural analysis, but also at the same time be reused and re-leveraged for thermal analysis. And that's something that's unique in the seamlessness of it compared to what some of our competitive tools might be out there. But with that, I'll hand it over to JF.
Thank you, Ganesh. Let's keep going. We'll focus on the space segment and thermal management specifically in the next part. I do want to remind everyone or tell everyone, we do have, if you have any questions during the presentation, we do have a question tab. So if you put your question in there, we'll make sure to address them at the end of the presentation or follow up with you by email if we don't get to it. So don't hesitate to use that. So yeah, space segment, specifically thermal management, is the focus today. And the tool for that that we're going to focus on today is SimCenter 3D Space Systems Thermal. It's a dedicated space thermal analysis tool, vertical of based on the TMG thermal solver developed by Maya. And the key features that enable it to solve your problems first, space thermal management are its solar heating capability, accounting for atmospheric attenuation. So if you're doing any type of rovers on the moon or on Mars, it's the tool for you. We also do articulating meshes. So if you have to do solar panel alignment, deployable structures like deployable radiators are a big thing right now on CubeSats, for example. We also have an orbit visualizer to verify your attitude, and we model the full orbit fluxes, solar, albedo, or FIR. We do have all the simulation objects, the simulation boundary conditions to model active and passive thermal controls, such as thermostats, PIDs, thermal electrical coolers, thermal coatings, DOL, EOL, heat pipes. And the big new thing that we have is GPU accelerated ray tracing. So you can go much faster when you do your analysis. We'll come back to that in a little bit. A little bit about TMG. So TMG is the solver behind Space Systems Thermal, and it was released back in 1984, and it was integrated in IDEA's TMG back in 1988. So it's been in the space industry for over 40 years now, and we've been improving it ever since by adding different physics, such as our 1D flow solver, 3D CFD, Joule heating, strong coupling with structural, with Nastran. We also have flow structural interaction, FMI, FMU co-simulation to co-simulate with system level tools such as SimCenter AimSim or SimCenter FlowMaster, for example. And we also have an add-on product called TMG Correlation, specifically for thermal model correlation to test data. So that one's the latest. So we have another poll question. So which thermal analysis tool do you currently use? So if you can give us an idea, we put on the typical thermal tools out there. So as you probably know, oh, okay. Some good voting participation. That's always good to see. It's going really fast, actually. And once again, a good spread. Interesting. So very nice. So some current users and some not current users. So okay, and
but it's the usual suspects. So it's good to see.
Yeah. Okay, great. So I'll share the results as well, so everyone can see. So yeah, for the ones not using our tools, hopefully you'll like what you see today and learn a little bit more about it. Okay, so I did have another polling question, so kind of related. As part of your thermal analysis, what's your biggest challenge when it comes to making, doing your analysis? So we put a few things. So geometry prep or CAD cleanup, meshing, reduced model generation. So if you have to send, I know one big requirement often is to send reduced models to launch services or for running multiple cases, especially for PCB models, you might create reduced models. Correlation, that one we're interested in because we do have that add-on product. We have TMG Correlation. I know it's quite man-intensive to correlate thermal models. There's a lot of unknowns such as contacts, optical properties, and Then you have model complexity and runtime, right? You want accurate results, so you make bigger and bigger models, but they take longer to run. So, oh, okay, interesting. So CAD and runtime, but once again, kind of all spread out. So,
Which is good.
huh,
Which is good to see.
yeah, very nice. Good participation too. Thank you, everyone. So enough questions. Now some more presentation. So as for those who are not using SimCenter 3D right now, your workflow might look a little bit like on the top. So you have your thermal tool interface, and then typically your CAD tool is a separate tool outside, which you'll interface with. You might even have a separate application for your CAD simplification and meshing, which you go back and forth with your thermal tool with. And then the thermal tool would usually generate an input file that the thermal solver runs. And then you do post-processing and maybe even another interface. So it's all very separate. There's a lot of back and forth, a lot of data transfer that can cause some issues. And that's where we, SimCenter 3D has a more streamlined workflow. It's all within the same tool, the same interface. So SimCenter 3D is CAD integrated. We'll look at that in the demo, but it's built on top of NX. So you're not going back and forth to a different CAD model. You don't have to. We directly do the meshing and the pre-processing all within SimCenter 3D. You have Space Systems Thermal, which is vertical specifically for the thermal analysis of space. And then you do all the post-processing inside SimCenter 3D as well. And all of that is iterative as well, right? As per your typical workflow. One such client that saw the benefits of going from a legacy tool workflow like that to the SimCenter 3D workflow. Well, they saw that something that used to take them weeks went down to a few days, and that's where the 83% came from. So Mynaric is one of our customers in Germany. They make laser communication system, and there's a blog post. So if you want to that link, want to read the full story, you can hear about it. The big things were the GPU ray tracing and the one environment for thermal structural. They do a lot of being optical systems. The thermal deformations are really important for them. So being able to do everything from thermal to structural in one environment was really key to them. And really the GPU was also a great feature. What they said, it's really awesome. And basically when they compared their results from the CPU to the GPU, they got exactly the same results, but much faster. So what used to take them weeks now takes just a day. So huge time savings. So some of the key features that enable Mynaric to be so happy with us, I would say, is the key differentiators for SST are that we leverage the CAD data. We're directly integrated into SimCenter 3D and NX. We have advanced simulation methods for all the level of accuracy you need for your thermal model, from very simple to highly detailed. We have a ton of different tools to parameterize your model and make running different cases a lot faster. And we have some automation to automate tasks, repetitive tasks, or tasks that are error prone within the tool. So we'll take a closer look at each one of these in the minutes to come. But out of those topics, which topic do you look forward to learning more about? So another quick polling question. So do you want to learn more about the CAD integration, the simulation methods, the parameterization, or the automation? Okay, we're a very homogeneous, oh no, more simulation methods. Okay, interesting. Let me share a lot of quick answers, everyone. Thank you for that. Okay, so let's learn a little bit about each one then, since everyone was kind of, it was kind of a little bit more on the second one, so interesting. So yeah, first off, leveraging the CAD data. So here's a video of SimCenter 3D with a spacecraft CAD model. This is just like the CAD interface. So you have the full assembly of the bus, star trackers, a boom with a deployable antenna that you see there. So that's the bus. You have some star trackers. You have some solar arrays, the deployable boom, and we have a payload with a Maya payload. It's a pallet with a couple electronic boxes and some CCHBs on the bottom that you'll see. So those are the two electronic boxes. And in the pallet, there's some grooves with some CCHPs, or constant conductance heat pipes, to keep the pallet at a constant temperature, or spread the heat out. So we'll directly leverage this CAD structure to build our thermal model. What we're going to be using is what we call assembly FEMs. Assembly FEMs are a similar concept to CAD assemblies. So each subpart or component can be meshed separately, which makes separating the workload a lot easier. So if you have different team members, they can mesh certain parts. What I want to point out here is you'll see all the different physics that you can, or solvers that are accessible all within SimCenter 3D. We'll be focusing on Space Systems Thermal today, but know that you have acoustics, you have Nastran, you have a bunch of different solvers you can access in SimCenter 3D. So based on the CAD, we make this assembly FEM, and each part, we keep the same structure as the CAD assembly, and we can import and position our FEM models or mesh models at the same position as the assembly. So it makes spreading out the load a lot easier for meshing. It also makes the model structure a lot more intuitive because you follow the same as the CAD structure. And you also can do breakout modeling. So you can do a simulation on part of the model and reuse that at the higher level. So what I'm doing here in the video is just positioning or linking the CAD part with the associated meshed part. So everything that screen means it has associated FEM with it. Here we can see we can do, what's nice is we can do sub-assemblies. So you can do assemblies of assemblies just like you would in a typical CAD part, but with finite element models. And what's great is that's all associative. So if you make any changes at the CAD level, those are all propagated automatically through to the FEM and the simulator on. So for example, here what I'm going to do is take this boom that is currently deployed, and I'm going to go and stow it using the assembly arrangements. So this is a feature inside the NX CAD. So you can go from deployed to stowed, which will modify the position of the CAD parts. And now we can update just by switching back to our finite element model, we can update that and be ready to solve our stowed cases. So by having that direct link between the CAD and the analysis model, it's really easy to stay in sync and quickly update your solution and have quick turnaround when you do your design over the life cycle of your product design. Our next topic is going to be on the advanced simulation methods. You want to be able to go from some simple assumptions, some back of the hand, really quick calculations, to all the way to the ultra detailed models, and SST and the TMG solver can handle that. So let's focus more on the boundary condition setup for this spacecraft. So first off, it's a satellite, so it's an orbit. So we have our orbit definition, which is here. We can specify what elements receive solar and fluxes. And then we can specify the orbit orientation, as well as different orbit types. Here we're using a fixed beta angle, but you could do different classical orbits or subplanet vectors. So we have the satellite Z direction directly pointing towards nadir. We can verify that in our orbit visualizer. So here we can verify, okay, I set up my orbit correctly. We can see, for example, that from the sun, it will never see in yellow, what you saw there were the radiators. So they're always seeing deep space, which we'll use to cool our electronics inside the satellite. So in yellow, the points are all our orbit calculation points for our sun, albedo, and Earth-IR fluxes. And we can switch from one orbit to the other. So if you have multiple orbit definitions in your model, you can view all of them inside the visualizer. Next, we have, so here in blue, we have the radiators. They're connected to our palette that we saw earlier, right? The palette with the two electronic boxes. They're connected through a loop heat pipe. You can model this loop heat pipe a few methods, the most detailed one being co-simulation with AIMSIM, for example, to do the full two-phase flow system. Or in this case, we'll take an assumption and do a temperature-dependent conductance. So what we're seeing is we have the two electronic boxes, loop heat pipe evaporator, and the CCHPs behind it. And so we have our MCU PDUs. There are some heat loads there applied directly to the boxes. And we then have our radiator. And what we'll do is we'll connect that LHP to the evaporator. Currently, it's a total conductance, a constant one, but we can make it directly temperature dependent. So we can put in logic directly into the tool. So you can do if, else, then. So for example, you can do if temperature of the the plate is higher than 20, use 0.1 watts per C, else use 20. No need to run or write like a complicated user plugin or a Fortran subroutine. It's all within the UI. For this case, we'll keep it constant. Then we need to model the constant conductance heat pipes in the palette. So there's 5 of them. What we do is we model the conductance in the pipe with 1D beam elements, and then we have a boundary condition to model the vapor node inside. and that will model the heat spreading effect. So for each one of these CCHPs, we have a conductance between the CCHP and the pallet, which we can view the connections in the UI, make sure it's connecting the right things together. And we can then look at the, so those are the connections between the CCHP and the pallet. And then we can model the CCHPs with a heat transfer coefficient to a fluid node. We can have different heat transfer coefficient for the condensation and evaporation side, or just override the total conductance. We have minimum operating, maximum operating temperatures, max temperature limits, all inputs that you would get from a constant conductance heat pipe supplier. And it's quick and easy to set up. Now, we're ready to run this model. We did two cases, one with the heat pipe, one without, to show you how you can compare two results. We have what we call results probe, which are graphs that are updated every time you run. You can quickly show them. So we're comparing the two electronics box temperatures, for example, with and without heat pipes. And we have pre-save post-processing views. So you can do contour plots and graphs that are saved. And if you rerun your model, those are all updated automatically. So here on the left, we can see the case without the heat pipe and the case with heat pipe. Obviously, the case with heat pipe is much cooler. You can see it's spreading the heat out much more towards the evaporator. And you can probe and see the temperatures in the graphs as well for both the electronics boxes. In addition to the post-processing inside SimCenter 3D, there's also post-processing in the solver output files. One of these, for example, is the BC data HTML. It's a HTML file that gets written during runtime that you can view and is interactive. So for each of the heat pipes, it gives you the heat pipe temperature, fluid temperature, but also the amount of heat that goes through each heat pipe. Gives you a summary of your groups of elements. So you can do min, max, average temperatures. For each of the contacts, the thermocoupling, you get heat fluxes. And all that data is in HTML and also in text format. So you can post-process in Excel if you want to as well. So for example, here we can see there's a lot more heat going through the middle heat pipes than the side ones, which makes sense. Now you can see you can go from, there's a different some examples of the boundary conditions inside of TMG and SST. Another big new feature that we have is the GPU ray tracing. So when you calculate anything in space, a big portion of the runtime is based on view factor calculation. That can take quite a bit of time. And typically we ran this on CPU in parallel, and it scales very nicely. So here we can see our CPU method on up to 40 cores scaled nicely, but it still took 6 hours. This was for a big coupled thermal flow, actually, a model that had around 200,000 elements. So it took about 6 hours just to do the view factor calculation on 40 cores. But with the new GPU ray tracing, it took just 8 minutes on one GPU, RTX 2080. And to give you more of a space example, these are two customer models that we ran with the GPU. So one was a camera in orbit, around 280,000 elements, 12 orbital positions, 2 radiation enclosures for the surface-to-surface radiation. And it also, being a camera, it had specular and transparent effects. And used to take 9 hours for the view factors, went down to 16 minutes on GPU, so 34 times faster. And for overall with temperature calculation, it was about 10 hours, and that went down to 1 hour, so 10 times faster. And a similar story with a full spacecraft model, so 130,000 elements, 9 enclosures. This one also had articulation and rotations of the solar panels, solar transparent effect, and we saw similar speed ups. So 9 hours, 40 minutes, 15 times faster, and 7 times faster overall. So dramatically faster. So really, you can see that the TMG solver is very flexible. It can easily accommodate, some simple assumptions or the full complex physics that you need to, you might want to simulate. Next, let's talk about parameterizing the model. So in space, as you know, you need to run a lot of different operational cases. So you might have your standby cold, operating hot, operating cold, your stowed case, some roll cases. And, in order to set those up quickly, we have what we call expressions in SimCenter 3D. So those expressions control values like the heat loads. Basically anything that has an input in the UI, you can create an expression for that you can control. So for example, we did expressions for all the heat loads, the orbit, albedo, Earth IR, things like that, and the MLI E-star. And with that, you can switch them from hot to cold, from operating to non-operating. And the best way to do that is with what we call the parameter table. So the parameter table is a way to set up a table of all the different cases you have. And you can base them off expressions in the model. So here we have all the orbit, MLI E-star, the heat loads, and we can add configurations in this table and switch from one to the other. You can build it in the UI directly, or you can do it in Excel as well if you prefer, and just import it from file. So you can quickly generate a table like this to run all your different cases. So if you need to go from hot to cold, you just change the operational, what's active. You'll see a green arrow, and it switches the values in the boundary conditions, like here. Here. So you see the little green circle means the operating hot case is active, and you can switch between them quite easily. Now, so you don't have to manually set up each one. You can just switch them all together with this parameter table. It reduces time and effort in setting up your analysis, and it avoids costly mistakes when you do. Finally, let's talk about automation. So you have probably a lot of tedious tasks that you do, and maybe we don't have that feature in yet to the software. Well, you have access to the NX Open API to automate all of that. So inside of SimCenter, which is based on NX, you have access to what we call NX Open. So basically, it's a journaling. So it can be in different languages. So C#, Python, Visual Basic. We'll be using C# here. What I did is I hit this record button. That means that every click I make in the interface now, it will record in this journal that I can replay. So what I'm going to do is go through the clicks of switching from a stowed to deployed arrangement, and it will register out those clicks and will create a journal I can then run. And instead of being 4 or 5 clicks to go from stowed to deploy, now it's a single click in the interface. So we went through these steps, we hit the stop. That generated a C# journal file that I can then open right here and edit. So right now it's hard-coded to go from stowed to deployed. But if I go down and find the specific line about stowed to deploy, right here, you can see it's hard-coded stowed. Well, instead of hard-coded, I can pass an argument. And what that means is now I can create a button inside SimCenter 3D that lets me do pass it an argument. So I can do stowed, a button for stowing and a button for deploying. So I can create a custom interface with custom buttons, all with different journals I made. So here I'm just creating a new tab and creating a new button, pointing to that journal file I did, and passing it an argument, so the deployed argument. And I can change the name of the button, the icon. And now when I click here, it does the deploying for me all in one click instead of 4 separate ones. So we're saving clicks, we're saving time, we're being more efficient. So if we fast forward a little bit, I made this whole toolbox myself. So I have separate buttons for stowed and deploy with matching images. We can do buttons to switch the parameter table. So going from different operation cases, or I made, for example, an NX Open script that does automatically beta sweeps. So that will run different cases for me. So the limit here is your imagination. Basically, anything you click, you can automate with the scripts here. Another type of automation is mapping. So as we mentioned, inside SimCenter 3D, you have access to different physics. One of those is structural analysis with Nastran. So you probably, if you're doing any thermal structural deformation, you want to take your thermal temperatures and map them to the structural mesh, which is obviously very different. Typically, thermal is very coarse because of radiation, and then structural is a lot more fine. So we have a mapping algorithm that can take those coarse temperatures and map them to the structural fine temperatures. You also have what we call constraints. So you can tell the mapping algorithm, okay, this is my solar panels, or these are MLI elements, I don't need them. This is our solar panels on the thermal side. These are the solar panels on the structural side. And it really constrains the mapping, so there's no mistakes in the mapping algorithm. And it's all within the same UI, so it's quite easy to work with the thermal and the structural model. No need to go to a separate other tool. It's all within SimCenter 3D. So here on the structural side, we're making directly in the Nastran model a mapping solution. We're pointing to the thermal results, and it will then take those thermal results, use the mapping constraints we created, and create temperatures on the Nastran model. So if you run the mapping, you now have temperatures on the Nastran model, and we create directly the Nastran DAT files that you need to run your thermoelastic distortion case. And you can plot them side by side and make sure there's nothing fishy going on with your results. Another automation, I won't go into it today because we don't have the time, but we also have a tool called NX PCB Exchange, made to model, really solve thermal and structural PCB level analysis. So if you're doing board level analysis, that's all automated with this tool. let us know if you want more details on that. We can do a follow-up webinar maybe, or just follow up with you by email. But it gives you the option to create this board level analysis, and then using the assembly FEM concept that we saw earlier, you can reuse that board level analysis directly in a higher system level. Maybe not the full spacecraft, that's probably overkill, but definitely at the box level, if you have multiple cards with the box, that's something that our customers do all the time and is very efficient with SimCenter 3D Space Systems Thermal. So yeah, we saw some examples of automation inside SimCenter 3D Space Systems Thermal. Automation is great because it eliminates mistakes and makes things faster, which is all things we love. So yeah, that's what I wanted to show today. We saw how we can leverage CAD to go update our models faster. We saw how we have simulation objects for all level of complexity in the model. We saw how we can parameterize our model for different operational cases. And we saw some examples of automation for different tasks, such as storing and deploying antennas, for example. And I just want to finish off on just last success story. One of our clients is Astrolab, Venturi Astrolab. They make a rover as part of one of the Artemis mission, and they use SST and Teamcenter and NX to reduce their iteration time as part of their bid to that project, and they were quite successful with it. So there's also a blog about it if you want to read more on that topic specifically. Yeah, we have one last poll question. So if would you be interested in doing a full day in-person workshop to learn more about SST? So I'll put that up. And meanwhile, we can also answer some questions. So if you have any questions, do feel free to put that in the question tab. We don't have a ton of time, but we have some time to answer. And if we don't get to your question, we can follow up with you by email.
And while you guys are answering the questions, I think one of the reasons we're asking for this interest, and it seems to be there is some interest in this workshop, is everything that JF showed you today and more. We can get into more depth about going through more systematically the different steps. And he talked about a lot of the different pieces that exist there, whether it's on the 1D side or looking at it from a PCB exchange. And hopefully we could answer any specific questions that you may have. And I think one of the key aspects, especially given where you guys mentioned what you currently use and with some of the competitive products, I think one of the big things is that with the thermal models, you have to take those and often have to take them back to a systems integrator and be able to have those reduced order models. And we have abilities to work with other tools for that maybe JF can talk to at some point. But yeah, we could get into all of that in an in-person event.
Yep. So there are a couple questions in the chat. So I guess by order of appearance.
You'll probably have to read them out, JF. So.
What? Sorry.
I think you have to read out the question. I don't think.
Oh yeah. Is AI circuit models already used in thermal analysis tools of SimCenter 3D? If yes, how the generated results are generated validated in terms of precision and reliability. Currently, inside of SimCenter 3D itself, there aren't any AI surrogate models implemented. However, in SimCenter HEEDS, which is a separate tools in Siemens portfolio, there is a AI builder assistant. I am not an expert on HEEDS though, so I'd have to, we might want to follow up on that if you want to get more info, but as part of the HEEDS tool, there is a surrogate model. The other thing we do inside of SimCenter 3D for Space Systems Thermal specifically is we often generate reduced models by order reduction. And we have the TMG correlation tool that is capable of correlating your reduced model to the detailed model automatically. And that's another way of creating a surrogate model that isn't AI based. And that one is physics-based, so it's a lot more transparent as to how it works.
Just a quick point on the HEEDS. So for those of you who aren't aware, HEEDS is our multidisciplinary optimization tool, which if you look at the examples that JF showed earlier with all the different parameters, whether it's based on CAD, thermal, and so forth, you can use them in a baseline model and you can look at a nexus of designs. And what HEEDS with AI does is that it's able to, so you might look at, if you were looking at it yourself, you might do like 5, 10, 20 runs. With HEEDS, you could go up to 500. But what HEEDS with the AI surrogate model is be able to look at, and rather than recompute 500 times, you can reduce the number of computations, but the AI surrogate model can look at those. So it's basically, generating these other kinds of designs based off of the same parameters using AI. But again, that's a different topic that we could, if there's questions and if there's interest, we can speak to separately.
Okay, maybe another question. How well do you think this workflow would integrate with other tools like SolidWorks for CAD or ANSYS for structural FEM? Good question. So for the SolidWorks part, so SimCenter 3D is based off of NX. So NX as a CAD itself is based on Parasolid, just like SolidWorks is. And so it actually has a direct import of SolidWorks files. You can just, without even an expert, you can just open drawing files from SolidWorks, and you can work on it just like you would NX native part. So it works extremely well with SolidWorks. And for the ANSYS structural part, inside SimCenter 3D, there's actually an ANSYS environment. So you can actually load up an ANSYS model. You can use SimCenter 3D to pre and post process ANSYS models. And as part of that, then we can do the mapping like we saw with Nastran, the same exact, the same way as with ANSYS structural.
I think there's maybe time for one more question, and then.
Sure. There's a question that's a little bit more like support, so I might follow up on that. Basically, for the question on so I guess on the question for the log files, how to get them to save in the same folder as the run files. Currently, they're always saved where the solver XML is. It doesn't go into the where the run files are. That's the way it works currently. Another question. Where are some of the best places for learning resources and tutorials for SST? So one thing I can recommend is the knowledge-based articles. So we're trying on the Maya side to add more and more to the knowledge-based articles. Um, and I can share, I think I can put a link in the chat. So I'll put a link into the chat to that. Or I can email it afterwards to the participant. But we do have a Maya help as well, where you can get some info. But also, if there are topics that you would like to, get more meat of it in the documentation, my email is right here. So if you want to contact me and you need some more examples, or I'm always looking for some feedback on the documentation and the tool in general. So feel free to contact me. And yeah, if we didn't get to your question, we will get back to you by email. We are a little 1 minute over time, so I don't want to. I want to be respectful of everyone's time today. So thank you a lot for attending, and yeah, we'll follow up with you if you have any questions we didn't answer.